So as I mentioned, I would like to occasionally introduce 3 minutes of culture into this. I used to tell you stories, but right now I decided I'll just occasionally play a song or something like that, very short one, which also would indicate what mood I'm in. So this is a song which perfectly reflects, first of all, it's a very, very great song by Franz Schubert, but it also perfectly reflects, I think, what will go on with the course and how I feel. The song is called The Organ Grinder. So let us spend a couple of minutes and listen to it. The singer here is, by the way, is Dietrich Fischer-Dieskau, maybe the greatest leader or art song singer of the last 50, 60, 70 years. He started singing in the late 40s, whatever. It makes it, how do I? So the organ grinder. Okay, so after we did a little bit of culture, let us do a little bit of programming. Some of you might remember that in our rush last time, we did not do really good job with rotate right by 1. We actually had to go, mark the things, pass 3 arguments instead of 2, use general purpose rotate, all because we didn't see how to write an algorithm for forward iterator, which rotates things to the right. Some of you, I know, actually figured out at least a solution. But I think the problem is quite instructive, not just because it's a useful algorithm, which it is, but because of the method we could use to derive the algorithm. So before we start coding, let us do a little bit of mathematics. Remember this thing, mathematics? I used to talk about it before they told me to switch to programming. And I'm looking for the blue marker. So let us think about the problem. We want to rotate right by 1 a sequence. First of all, if we have an empty sequence, what is it? We're done. Yes, we're done. Let's do one more. If we have a 1-element sequence, A sub 0, and we want to rotate it. Anybody knows how to do it? Done. Okay. So, and that allows us to consider an inductive solution. So what does it mean? We have to assume that somehow, by hook or by crook, we have an algorithm which knows how to shift things from A sub 0 to A to n minus 1, which is n elements, right? And then the question is, how could we get an algorithm for A sub n with 1 more element? Right? Now you see it. You should have seen it yesterday.
But that will still do 3 assignments per element.
I'm not saying that it's going to be faster than what you and Hernan did. I'm going to say that it's going to be much more elegant, because it's not going to have what you do in the beginning, it doesn't have to do anything at the end, and it will be sort of mathematically derived. So, right? So, there are multiple things. It's sort of, you could just hack a code, or you could try to derive it mathematically. And deriving mathematically is a good activity sometimes. So we know now that we somehow could do it up to n minus 1. So we start with our sequence a sub 0 dot 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 a sub n, and we know that we could apply our solutions by inductive hypothesis, and we're going to shift first n elements. This is n plus 1 element. Right? So we're going to shift first n elements by 1 to the right. So what are we going to have? We're going to have a n minus 1, right?
I think it would be a lot clearer if you just went through the 2-element and the 3-element.
I will. I will in a second. A sub 0. You know, since I invest all this thing, so a to the n minus 2, and then a sub n. We could do that, right? Now, what else do everybody? It's a sequence which sort of moved the a to the n minus 1 to the front, and still has a sub n at the end. So what do we need to do? Yes, swap of these two elements will solve the problem. So we need a swap of a sub n with the our first element. Right? So, and then we could figure out, so Param suggests that I show it with an example of 3 elements, which is a good idea. 1, 2, 3. So let us assume that we swap 1 and 2. So it's 2, 1, 3. And then we swap 2 and 3, and we get 3, 1, 2, which actually exactly what we need to do. Right? Do you think we could write the code now? It's in insertion. Let us go and fix. So we're going to right now we need to do a lot of work fixing insertion sort. But before that, let us go and fix this guy. So if you open insertion sort.h, you could obviously delete all the stuff, and we might as well fix the interfaces right away. We do not need but last. That we were doing out of necessity to be able to. Yeah, in all the
right, in the bidirectional case.
Yes, in bidirectional case, it's very easy. Well, no, it's but last and minus minus but last. Okay, so we fixed. We'll need to recompile and see if it works. But right now, let us see how we do it for Ford. Again, here, obviously, we have let us ignore how we initialize that. But the fundamental code is going to be something like what? Anybody could? I claim it's a one line. While, yes, it's going to have while. Oh, come on, somebody should just risk it. I don't think so. As you see, we need to keep first because we keep reusing first. No, I say the main code is going to be. You guys sort of ignore that. Let's write the loop. Then you will make the beginning to make the loop correct.
So we have to swap, basically, right?
Yeah, something like that. And then you need to figure out, no. That, okay, the permutations, you tried all of them. So that's the one which will remain. And of course, now you have to figure out whether you're going to say plus plus current here or current plus plus here. I suggest that you put it here. Do you agree that's basically, we'll do that? We keep. And here you need to do bunch of routine stuff. Sort of, remember? That's what you actually need to do. I mean, you know, the base case. We actually do not need, we could skip the next. This is a decision which we should make. Do we really want always to swap first with itself? It's not going to hurt.
You're not doing it.
We won't, because we do plus plus current.
Yeah, so should go down.
We're going to skip that case with the level.
We're going to skip.
We're going to move to the second element.
We're gonna do it in.
And then if that equals last, once we do the plus plus here on the first condition, we're just going to exit. If there's one element.
Thank you, guys. Thank you, guys. Yeah. Okay. You have to agree it is very elegant. Again, you know, the problem is you have to try and try and try and try again, and use mathematics occasionally to get the correct algorithm, right? So now let us do one very simple thing. Now let us go and compile our test and look at the results. I mean the test sort. What I do? Because you forgot, yes? The reason I want to look at it is even now we're going to see a remarkable fact.
But hold on, the code we change is for the forward iterator.
Yeah, no. The code we changed is not affecting anything. But we never did that in the class. So I never had a chance to point you to a rather interesting observation. Ignore all the columns except this and this. Did you say -03? You got a totally different result from what I got. Okay, so in any case, the interesting fact is that these two columns, even here we have slightly more, about 15% of memory. We're still performing pretty much as if we have all the memory we need. All right? Which sort of shows, here we're of course running slower, but here we're running with, roughly speaking, 1% of memory. Between 1 and 2%, 1/64. Okay? So let us see, again, our task eventually is to get our guys as close as STL guys, or preferably Bitium. Right? One of the things which we need to consider is that we're using binary insertion sort. And since our cutoff point is relatively small, it's not clear whether binary insertion sort is the right algorithm to use at all. Right? If we have bidirectional iterators, we could use regular insertion sort, which is a very good algorithm, and we'll need it later in the course. It's a very, very important component to be used in multiple places, not just here. For example, when we implement quicksort, if we live long enough to do that, we will see that insertion sort will be very, very helpful. Plus, we will be able to investigate several interesting techniques and discover one deep problem on this very simple sorting algorithm. So let us go back to insertion sort and do some more work. So I want to spend some time on insertion sort. Right? Let us look what we have. So we have, if we go down, where is insertion sort itself? This is binary insertion sort. So binary insertion sort does find upper bound, and then shifts things and sticks the result there. Right? Simple, simple idea. The problem is that this is not always a good thing to do. Why? Because remember, insertion sort is good sort when things are almost sorted. What does it mean they're almost sorted? It means that they're pretty close to where they should be. And binary search is going to poke far away. Yes, it's going to do little poking, logarithmic number of poking. But it's going to poke too far. So since in very many cases, we're going to be using insertion sort in the context where, things are pretty close, doing linear insertion when you're not attempting to go far and check, might be a good thing to do.
So just to understand, what are your reasons for, I don't quite understand why you want to do linear. I mean, I have a reason that I'm thinking of. I don't know what reason you're thinking of.
My reason is, okay, let me use the board. Okay. So clearly, career as a juggler is not for me. So let us assume that we have an almost sorted sequence. What it means that when we're inserting this guy into the previously sorted thing, he's not going to travel far.
So you're saying if we have a bidirectional iterator, we should just look backwards to find the right spot.
Since we can. Because this, there's some distance, delta. Right? And if this delta is small on the average, then instead of doing poking in the middle, poking at the 3/4 and so on, is actually waste. Plus, it's a more complicated code. However simple our upper bound n is, which is pretty simple, it's still not as simple as just doing linear search.
The other reason I was thinking of was, since we are only doing this for small ranges, something like 16, 20.
That is not clear. Here we are. But in general, insertion sort is very good even for large ranges, as long as the average distance between where elements are and where they should be is small, which, as we discussed, means smaller than log n. Right? But in practice, we could reduce it, for example, if we somehow sort things that everybody is within, say, 16 steps of its final destination. We could just run an insertion sort on a big thing, and it will do just fine.
And I mean, even if the linear scan does more comparisons, it might be faster, because 4 hard to predict branches, I suspect, are much more expensive than 8.
Yes? 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 Again, the linear insertion sort is particularly beautiful. In which case? When it's really optimal.
Sorted already.
Sorted array. Because then you look to the next guy, okay, you look to the next guy. I mean, yes, you do one comparison per element. Right? If you do binary insertion, you do lots more. So this I'm just explaining sort of with algorithms, with components, you have to literally sort of know the bunch. It's sort of metaphor which I have been using all my life. It's like a chess tool, a good woodworker doesn't have just one kind of tool. You have a bunch of tools, and you sort of look at your problem, whatever you're making, a door or whatever you make, and then you find the right tools. In some sense, I claim the goodness of a programmer is literally the best measure is the number of tools he is fluent with, the number of algorithms he is fluent with. Right? It's not, again, there is a very erroneous point of view that a good programmer is a person who could invent new algorithms. No, this is good, but most people don't need to invent. I mean, a good carpenter doesn't invent new tools. You could be an exceptionally good carpenter, world class, without ever introducing a new woodworking tool. But sort of one of the things which you need to know is existing tools. And what I'm trying to urge everyone is that, we need to constantly try to increase the amount of tools, even little tools like rotate one to the right. Everything like that will come handy. Of course, I constantly hear, this is a thing which I hear all the time, but I never needed a given algorithm. Well, this is true, and every carpenter never, for a given day, doesn't use a given tool. Nevertheless, they have a large tool chest for those cases when they need it. Right? So larger the tool chest, better off you are. Easier it is going to be to solve problems. Moreover, again, if these tools are known to everyone, other people could understand what you do. Again, this is why I'm trying to come up with a systematic set of components, because I think it's I actually think programming is a wonderful thing if you know many algorithms and data structures, and just use them. Okay. This is a little sermon. I have to sermonize occasionally. I have been omitting this thing lately. But so let us try to write insertion sort n. Either 2 loops or a subroutine. Again, we have to always think in the following sense. Couldn't we take something and turn it into a subroutine? Because you know, maybe people could use it in other contexts.
So find partition point.
Well, we want to be swapping as we look for the right spot.
For example, that's a good idea. But which subroutine am I talking about?
Swap yourself to the right spot.
Yes, now find a name for that.
Seems like it's probably into the right position.
I think, yes, I think that's a very good name. Insert. He tried to be unoriginal, which is exactly what you want. You want a name. What are we going to do? We're doing insertion sort, right? Which is a bunch of insertions. So if we have a function called insert or linear insert, because this is basically binary insert. So maybe what we should do to fully sort of follow Nick's suggestion is try to see whether we could factor that out before we even work on linear insert, whether we could have a thing called binary insert. Because then our binary insertion sort n will be just a loop which is doing binary, you know, this is combination of these two things. Could we do that? Maybe we'll learn something. You think we'll learn something? Okay, anybody wants to lead the battle? Bert, you want to lead the battle. You're anxious to do it. Should I give him the
Spoon.
Sit down.
It's probably you want to put a new thing on line 34, which probably is going to have pretty much line 35 to 39.
We'll call it binary insert. Insert n.
Insert or insert n. Observe here at this point, we do not really use n. I'm just pointing.
We use first. We use I. We use the value.
By the way, just to simplify, could we take a look at this guy for a second? Somehow, where did it disappear? No. I say binary insertion sort. Okay, what we clearly missed here is that we could write plus last and eliminate line 15.
We had that before, and then we changed it when we were doing the but last and stuff.
Yes. But when we changed this sort of shows
We should call it binary insert n.
should we? How we're going to use it here? Let us, okay, first of all, it's Bert's turn. Second of all, let me suggest something. Wouldn't it be the right thing, before we write this piece of code, use it here? Because that will answer all of our problems. we will see whether it's n or whether we need n or not.
We call binary insert and check it. That's it, right?
Yes. The question is, what argument does it take?
First I and
Last.
star last and R. Is that too much?
First I.
I think we need star last or last, one or the other. Oh, actually, we need last. Yeah, for rotate right, we're going to need last.
Or, yes, for I don't even understand how this code works, guys. I apologize. I don't understand how we managed to sort, which we did. Insertion point. No, but because we're moving last. Last starts, yes, now I understand how it works. Probably last is a very bad name, guys, because that's why I was having problems now. And I think if we replace it with current, no, because it's current. Yes. And by the way, we need to work a little bit more, guys. So we really could skip. We could first element. Everybody agrees with that? So we could do plus I here. And we could do plus current here. And then drop it here. Right? So at least now, what we see is that this binary insert will actually need 4 arguments. Am I correct? Yeah, because it needs current. Otherwise, we'll have to compute current. We cannot afford, that's too expensive. By the way,
Since I and current are related to each other, but computing either is expensive, and so we want to pass both.
guys, we made lots of changes. Let's comment line 50. Let's comment the other guy. And let's recompile. I'm right now losing it. By the way, I have a good news. From now on, we're going to have only pizza. M-Team decided that there is about what they want to feed us. But they haven't yet decided that it's going to be cold pizza from yesterday. So we're still going to get warm pizza. But you just wait. Yeah. So let us go and see what we we're doing upper bound from first to I plus current No, this is all right. It could be outside the range. Yes, and what's wrong about that? So we need to look at the second guy. No. We know now that it is at least.
If it's 1, then we can only dereference first, but we just plus current in the second element.
So let us put 1 in there. And let us think. This check is going to be utterly unneeded. Yeah, let us do, for insertion sort, let us do our standard checks. Let us truly say, as you know, if it's.
No, this will work though, right? If this is 1, then this becomes 2, and if this is 0 or 1, either case we're going to return current, which is either going to be a bad iterator or just the.
It cannot be. I mean, it's incorrect current.
But we're going to plus it here to make it the correct current.
Not if we drop out of while. We have. I recommend that once and for all we do what we should be doing is to say, remember our precondition that if it's empty or if it's one element guy.
In the loop, I is the number of elements that have already been
Yes.
put in position.
Yes.
And then current is sort of the next one after that.
Plus current, and but maybe this we don't need. Maybe that now works.
But this still needs to be.
Plus. No. Now it needs to be incremented because that was 1.
But we can't dereference it.
No, because we know that it's less than 2. Less or equal. We know that it's at least 2. We know that it's at least
When we
2.
call upper bound, that I parameter, we don't want it to be 2 the first time. We want it to be 1 the first time. There's only one element in place.
Let's go eat pizza.